Hi, everyone. Welcome to the webinar, Manufacturing Horizons, AI Applications, including Enhanced Process Control. It's great to see so many people from across the world registered for this webinar today, showing a real interest in how AI can be used in manufacturing. Thank you for taking the time to attend. My name is Rob Driver. I'm the Marketing Manager for IFM Engage, which is the knowledge transfer arm of the Institute for Manufacturing, and I'm the host for today's webinar. So just moving on to a bit of housekeeping before we get into the content, I just wanted to run through a few things. We're recording the session and it will be sent out to everyone that's registered for access. Please can you use the Q&A functionality to pose questions to our speakers at the end, and please do this throughout the webinar if a question pops into your head. And you can also use the chat functionality if you've got any technical questions, and we'll do our best to help. So just going on to a bit about the Institute for Manufacturing. The IFM is part of the University of Cambridge's Department of Engineering. We conduct research across a broad range of manufacturing-related topics under three broad strands, which are management, technology, and policy. We conduct education programs, both undergraduate and postgraduate education. And we also do a lot of extensive practice work, working with organisations to transfer and apply emerging tools and research through consultancy courses and memberships. A lot of this is done through the knowledge transfer arm IFM Engage. Throughout all of these strands, we work extensively with organisations across academia, government and industry. So just moving on to the next slide. Delighted that we've got two experts in AI today to speak to you. Professor Ajith Parlikad, who is the Professor of Asset Management here at the Institute for Manufacturing, and Associate Professor Sebastian Pattison, whose expertise is in manufacturing processes, systems, organisations. He's also from the IFM. So just going to our agenda, Ajith will be talking about an introduction to machine learning and artificial intelligence, and then we're moving on to introduction to AI in manufacturing processes from Sebastian, then on to some Q&A before closing the presentation. So I'll hand over to Ajith to start the presentation.
Thank you, Rob. Hopefully you can hear me loud and clear. As Rob mentioned, I'll spend the first 15 to 20 minutes talking about machine learning and artificial intelligence from in a general manner, just to provide you with an introduction and a flavor of what these words actually mean. And then Sebastian will go into the specifics of manufacturing processes. We'll have some time for question and answers at the end. So just to kick off, what is machine learning? Now, I'm sure a lot of you who have signed up for this webinar would be familiar with these terminologies, but I just thought it'll be good to provide a bit of context and definition at the start. There's no single globally accepted definition that you can find for machine learning, but there are some examples of definitions, as you can see on the screen here. On the left top side, you can see a general definition of learning. So learning is any process by which a system improves performance from experience. And below, what you can see is one of the early definitions of machine learning, which is it's a field of study that gives computers the ability to learn without being explicitly programmed about what to do. So that's the key thing about machine learning. It is about how a system learns a task, learns how to do a task, and improves its performance with experience or with historic data without being explicitly programmed about what to do. And that's the definition, or the description on the right-hand side of the screen that you see there. That is what it tries to illustrate. So a computer program is set to learn to perform a task from experience if the performance at that task, by using some performance measure, it improves with experience over time, right? So that's in general what machine learning means. And in that context, what does artificial intelligence mean? Now, if you talk to people out in industry, if you read articles about artificial intelligence and machine learning, one of the things that you keep seeing is that these two terms are often used synonymously. They're interchangeably used. There's nothing wrong in that, but I'd like to just use this opportunity to clarify, at least in our understanding, that there is some difference between machine learning and artificial intelligence. Machine learning, as we heard earlier, it is the process by which computers learn a task. Now, artificial intelligence is something that we are trying to achieve still. It is about creating a machine that can think and act like a human and do things like a human, right? We haven't yet achieved that, but in some respects, some small problems, we do have examples where we have been able to create artificial intelligence. And machine learning can be a part of artificial intelligence, especially where this intelligence is derived through a process of learning. And because it's learned by a machine, we say machine learning is part of artificial intelligence. But there are artificial intelligence approaches which does not use machine learning, rule-based approaches, inductive reasoning-based approaches, and so on for artificial intelligence. They don't necessarily use machine learning as a basis for it. But most of the techniques that you see today are based on machine learning. And that's why these two terms are used in a interchangeable manner. You can also see in the slide Alan Turing's vision, which is quite an early vision of what an artificial intelligence machine is. And what he was saying is, instead of trying to teach a computer to do things, teach them how to do things, why don't we try and develop a program or a computer that can simulate a child's mind? Instead of trying to get it to learn like an adult, try to get it to learn like a child. If you get a program to do that, then the program will just learn by itself. That's how children learn, right? So that's the vision, and that's the goal of artificial intelligence. And as I said, in some respects, it's achieved, but not in all respects. So let's move on to, with that basis, let's move on to manufacturing and some of the problems and some of the examples of artificial intelligence and machine learning. So before we get into that, we might wonder, why are we doing this? So as manufacturing engineers, we all have different questions that we are interested in, but what I've tried to capture here are some common sets of questions that any manufacturing organization might be interested in getting answers to. So right from the early stages of your raw material supply, you might want to know, which suppliers should we choose? Where is my stuff? How can we track our products through the supply chain? How much do we need to order? When is it going to arrive in my factory? During manufacturing, we always have to decide, what products are we going to make today? How much are we going to make? We've got machines in our factory. How often do we need to, when do we need to maintain them? When do we need to replace parts? Of course, the products need to be sold. And for that, we need to answer questions such as, what kind of sales channels do we use? What kind of promotions are working? Which promotions should we stop and not working? In terms of after sales, we want to keep understanding, we want to keep learning how our products are being used by our customers so that we can improve our designs. We want to make sure that our products last long and keep providing the service that the customers are expecting them to provide. And if they are not, we need to provide that support to our customers. So what warranties should we give? So there are a lot of questions that manufacturing organizations are constantly asking themselves. And all these techniques, including machine learning and artificial intelligence, are about providing better answers to these questions, or approaches to provide better answers to these questions. And in most machine learning and artificial intelligence approaches, the fundamental foundation for all this is data. As I said earlier, there are some techniques that do not depend on data, about rules and so on, but mostly we are talking about data-centric approaches. So what are the kinds of data that we see in manufacturing generally? So some of the common sources of data, for big manufacturing companies, you've got your ERP and MRP systems. For most machines are monitored, so we'll have our statistical process control (SPC) data. When things fail, you might be keeping notes of it. When are things failing? What did we do when a machine failed? So you have your maintenance logs, your sales data. In the retail sector, you have got loyalty cards like your Tesco club cards and so on. And other data like customer service data, warranty claims. So there are a number of different types of data that we have at our disposal, and we'll be doing some kind of data analysis to derive some insights about how different operations within a supply chain are working, and use those insights to improve our decision-making process. What you can see that is common amongst these data sets is that they are fairly structured. In the grand scheme of things, they are of low volume, low velocity, low variety. Of course, you would think that there is a lot of variety amongst this, but when you think of the emerging sources of data sets that you see, social media data, sensors that you might slap on machines to monitor their condition, weather data that might affect your production plans or your sales plans in terms of whether you're going to sell salads or whether you're going to sell burgers today. Smart products, which are constantly being monitored, can do innovative stuff, will be sending you data back. So there's a lot of new types of data that we are dealing with in this world today. And what you see as different to the traditional sources of data are that these kind of data are very unstructured. So social media data, people commenting, chatting, posting pictures and so on, very unstructured compared to the traditional sources of data. High volume. So if you think about Twitter, billions of tweets every day, right? And we must develop new techniques to analyze and learn from these kind of data compared to the traditional sources of data. In this context, you might have heard this term big data as well, and this is what it refers to: high volume, high velocity, high variety, and there's an issue of veracity of data or the truth of data as well. So that's what we call the big data challenge these days. Okay, so that's a bit of a context. What I'll now take you through is a number of different types of machine learning approaches that you will see and hear over the course of this webinar and the subsequent webinars as well. So I'll use some common examples that we can all understand to introduce these different types of learnings. So let's look at this problem. You've got a series of numbers and they correspond to a single digit on the right hand side. So 1, 2, 3, 4 is equivalent to 1, 3, 8, 5, 5 is equivalent to 3, 7,690 is equivalent to 4. So looking at this pattern, I'm not going to ask you to respond to this as a question. Just think about what could be the possible answer to the new example. So 9,045 is equal to what single digit number? Now, if you spend just a few seconds looking through the patterns, you will soon realize that the right-hand side single digit is actually the sum of all digits of the left-hand side number. And in some cases, you might have to add up the digits of the two-digit number that you get derive at the end as well. So in fact, the answer to the last question is 9. So 9045 is equivalent to 9, right? So what you're try to think about what we are trying to do here in order to derive the answer to the final question. We are trying to figure out a pattern, right? So in our brain, we are trying to figure out a pattern and apply that learned pattern to a new problem, right? Another example. So that's the data that is given to you. The first three things. So the solid red square is yes. The solid green circle is no. A solid red circle is yes. So what would be a hollow green square be? Now, I'm sure you might be thinking of the answer at the moment, and I'm sure some people are thinking, okay, green could mean no, but then a square is yes, but then a circle is also a yes. But so how do I answer this question? So what I want to highlight here is that this kind of a problem, or this kind of a learning where we are trying to learn a pattern and then apply that learned pattern to a new problem, is called supervised learning. So in a supervised learning problem, what you're given is a set of what we call training examples. So in the case of digits, you had 3 or 4 different examples, which allowed you to kind of establish the relationship between the input data and the output, what you're expecting to provide as an answer. In machine learning terminologies, we call this input information features, and the answer to the question as labels. So in a supervised learning supervised type of learning, what you're given is a set of examples where you have got the features and you've got the correct answers or the labels, and then based on that you learn and then try and predict the answers to the questions that you don't have answers to. So in this case, the features as the input to the machine learning problem might be the color, the number of corners in the shape, or the shape itself, or the size of the shape, position, orientation, and so on. And the labels are the yes and no answers. And the machine learning algorithm is trying to establish the relationship between these two. And often the question that you ask then immediately is, how many training examples do we need to have in our hand in order to establish that relationship in a fair level of confidence? So in the first example where we are trying to relate the two numbers, it was sufficient to have 2 or 3 examples before which we could establish the relationship. But then in this example with the square and circles, perhaps we are not given enough data. Based on the given data, you might be able to say, okay, I think the answer is no, but you might say we need more training examples, right? So this is the first type of learning, machine learning, which is supervised learning. And some of the examples that you see in the real world where this is applied to are facial recognition. Now I'm oversimplifying this a bit by saying this is a pure classification problem. In a facial recognition example, you need to be able to locate the faces in a big picture and then identify where the features of the face are, and then identify the face and classify that as a particular person. And this is where this terminology classification comes in. So this type of problem is called classification, and it is the type of learning that you use to address the classification problem is called supervised learning. So you're trying to classify the input data into some categories and then try to identify which category or which classification does a new data set belong to. On the right-hand side, you see an example from manufacturing where we are trying to identify defective bottles. So you'll see that this algorithm has identified the bottles that is coming off a conveyor belt, but it's also identified a particular the bottle with a cap which has got a crack on it. So it is an anomaly detection or a defect detection problem. So again, this is a classification problem, and the learning process is a supervised learning process. This is a very popular example. These days, we all talk about
farther ahead on the right,
autonomous
the bounding
vehicles.
box on traffic light. You see a green line on the lane mark. And you see also the pedestrians, even those on the side, are being detected. Also,
so what you can see here is what an autonomous vehicle is seeing. So what as the vehicle passes through, it is trying to pick the different things that it can see and classify them as vehicles, pedestrians, and so on, traffic light, and so on, so that the vehicle can then make appropriate decisions based on what it is seeing. But then one of the fundamental things that it needs to address is this classification problem. But of course, an autonomous vehicle runs a lot more complicated algorithms in order to make it work. Right. So moving on. So that was one type of problem that we can use supervised learning for. The other type of problem is called regression. And regression is where you've been given some training examples, training data. So for example, here we are trying to predict the cost of usage of a particular component in a vehicle or in your factory as a function of time. As time progresses, its efficiency, for example, drops, so the cost of operation keeps increasing. You might be collecting data that allows you to learn the relationship between time and cost. So you collect some data, use that data, and apply this technique called regression to predict what the cost might be in, say, 20 days time. If you've collected data for the first 10 days, based on that, how can you predict the cost of operation in 20 days? So that's a regression problem. A similar kind of a problem is in maintenance, where we are trying to estimate the reliability of components. So here we don't have a single one-dimensional problem where we are trying to predict something just based on time. So in this example, it's based on an aerospace engine where we are trying to predict the probability of failure based on the number of landing and takeoff cycles and the number of flying hours. So instead of a line, we have a surface, and using that surface, we try to learn that surface and use that surface to try and predict when things are going to fail. So that's a regression problem, again, learned using supervised learning. Another type of learning, this is the second type of learning, is where you are not given the answers to the question as within your training data. You're just given a data set and asked to try and make sense out of it. So a typical problem here, you're given, say, 5 pictures and asked to pick the odd one out. So immediately we can see 3 of them are fruits, 1 is a sock, so the sock is the odd one out, right? Again, think what we are trying to do in our brain. Another example, set of keys. How do you group similar keys, right? Immediately, I'm sure some of you might come up with a different grouping than the other. One grouping is, okay, you group all the golden keys and the one that looks more silver, and in 2 different groups, right? Some of you might say, oh, I was actually thinking about the one that looks a bit ancient and decorative, and the group of keys that were non-decorative, right? So there are different groups, but we don't know what the correct answer is. And this type of learning is called unsupervised learning, and the type of problem we try to tackle using unsupervised learning, one of the types of problems is called clustering. So you try to cluster similar stuff using the data that you're given, right? But the issues here is that how do we define similarity? So as we said, it's similarity defined by the color, or similarity defined by the shape and the decorativeness of the keys. How do we know how many groups we need to group them into? So here we have grouped them into 2 clusters. How do we know there are 2 clusters or 4 clusters or 15 clusters, right? So there are some issues that there are techniques to resolve within the machine learning set of approaches. So this is the second type of learning, which is called unsupervised learning or clustering. And a typical example of where we might use this in the context of manufacturing is, so here I've used this in the context of predictive maintenance. So we are monitoring a machine using a sensor, and it's the sensor values that you can see on the left-hand side. And these graphs that you see there are the sensor values that lead up to failure. So everything starts off similarly at the early stages. As the machine ages, the sensor values change its patterns over time, and then the machines fail. Now you can see that from the graphs that not all of those machines are actually behaving similarly before it fails. The obvious kind of patterns are some of the sensor values are increasing before failure, some of the sensor values are decreasing before failure. But even within that, you might see that not all machines, they're not homogeneous. So we might want to apply a clustering technique to identify similar machines so that we can learn the patterns for some clusters of machines. And what we can do with this later on is identify when you have a new machine, try and identify which cluster that machine belongs to, and then for that cluster, try and fit a user regression model to try and fit try and use a regression algorithm to try and predict when that machine is going to fail based on all the historical data of the machines in that particular cluster. So you're kind of combining a clustering problem with a regression problem to address the issue of predictive maintenance. Yeah. The final type of learning is what we call reinforcement learning. And this is a type of learning where we don't tell the machine what to do or how to do. All we do is to provide the machine or the program a kind of reward when the machine behaves in a way we want it to behave. And sometimes we give it a penalty when the machine behaves in a way that it doesn't want to behave. All we say to the machine is, your job is to increase or maximize your reward. And the machine figures out a way in which you can maximize its reward. And this is similar to how most human beings and animals learn. So there's some examples in this slide where people in Africa have trained rats and mice to detect landmines. This second example where a pigeon is being trained to detect or identify breast cancer in humans by providing some kind of reward for a positive action that they take. This is a good example to show how reinforcement learning works in the context of machine learning. So I'll leave the video.
So I'm going to show you a couple of fun videos of these agents at work. But before I do that, I just want to be very clear to you what you're going to actually see and the significance of that. So we started off with classic 8-bit Atari games from the 80s eras. So these are very iconic games that many of you will be familiar with. But here, the agent, the system, only gets raw pixels as inputs. So it gets about 30,000 numbers per frame, per 50th of a second, because the screen resolution for Atari games was 200 by 150 pixels, roughly. And the goal here that we give the machine is to maximize scores. It's a simple goal. And everything else is learned from scratch. So it has no idea what it's controlling. It has no idea it's playing a game, of course. It has no idea about the rules of the game. All it's getting is these raw pixels as data. And then the last thing is we enforce this idea of generality again. So a single system being able to play all these different Atari games, and there's hundreds of them, out of the box. The same system without any changes. So I'm going to show you a couple of videos. So the first one is Space Invaders, probably the most iconic game on Atari. And I'm just going to roll this video, and the sort of first part of the video shows you what the agent does when it first sees this data stream. So it's literally the first time it's ever seen these numbers, these 30,000 numbers. And you can see it's controlling the green spaceship at the bottom of the screen, and it's losing its 3 lives immediately, because it basically has no idea what it's controlling in this world or what it's supposed to do. Now you leave this system playing on a single GPU machine overnight, you come back the next day, and now just through self-play, it's now superhuman at the game. It's better than any human can play Space Invaders. So you'll notice it can't be killed anymore by the enemy Space Invaders. It's worked out the pink mothership at the top there is worth the most points. It does these amazingly accurate shots to get that. And if you, for those of you who play Space Invaders, you'll remember that they get faster as there's less of them on the screen. If you watch carefully the last shot the spaceship fires. So it makes this kind of predictive shot as to where that Space Invader will be in time. So it's kind of implicitly modeled this world accurately enough to understand what the movements of these enemy ships will be doing ahead of time. So this is my favorite video. It's called Breakout. And in this game, I'm just going to show you more gradations of the agent getting better over time. And in this game, you control the bat and ball at the bottom of the screen, and you're trying to break through this rainbow-colored brick wall, brick by brick. So this is after just 100 games of play, and you can see the agent is pretty terrible at playing this game. It's missing the ball most of the time, but you're starting to get the hang of the idea it should be moving the bat towards the ball. Now, after 300 games, it's about as good as any human can play this. So it almost always gets the ball back, even when it's coming back at very fast angles. So we thought, great, this is cool. But what happens if we just leave the machine playing the game for another couple more hours, couple more 100 games? And to our surprise, what it did was it found the optimal strategy was to dig a tunnel around the left-hand side here. You can see it sort of superhuman accuracy, getting the ball back round the side and getting it behind the wall. And the funny thing is that the amazing researchers, you know, who created this algorithm, they're brilliant researchers, but they're not so good at playing Atari. And they didn't even know about that strategy. So, you know, maybe it's the first example there of something unusual where the creators of a system were actually taught something by their own system. And that entire stack of problems.
So hopefully that's given you an idea of what reinforcement learning can do and is. It's a very exciting video. The last concept before, hopefully that has given you also an idea of what machine learning means, the 3 types of machine learning and the different kinds of problems we can actually address using machine learning. And before I hand over to Sebastian, I thought it might be useful to talk about one more buzzword that you might have heard a lot in this context, which is digital twins. So just to cover that off, digital twin in its simplest definition is that it's a digital replica of a physical entity or process. Now, digital twins have been talked about and have been around for a bit. NASA had talked about digital twins early on, and it was in the context of its spacecrafts and so on. But these days, we are talking about digital twins in the context of manufacturing, in the context of supply chains, in the context of everything around us, right, in infrastructure and so on. What we need to understand is that there is a fundamental difference between a digital twin and any digital model. So that's the first question people ask: what's the difference between a twin and a model? What differentiates a digital twin from a digital model is that a digital twin has got a connection to a single physical counterpart. So it's not just a model that represents a type of a car. It is a model that reflects or represents a single car out there that is running. And there is that physical connectivity, data connectivity between the physical twin and the digital counterpart. And based on that data, the digital twin can make some decisions and hopefully feed that back into that physical asset as well. And that's what makes a digital twin, which is that two-way connectivity of data and decisions between the physical and digital counterpart. I'll stop my my section here in the interest of time and hand over to Sebastian, who will be talking more in depth about process control and how artificial intelligence can be used in that context. So Sebastian, do you want to take over from here?
Yep, sounds good. If you could stop sharing your screen, then I will stop sharing mine.
Yeah. Go ahead.
All right. There we go. And well, I hope everyone can see the screen. So
just quickly, if you just share your other screen, because we're just looking at the slide deck at the moment.
Is that the right one?
Yes.
Fantastic. Okay. Well, to start off with, I just would like to wish everyone a very happy National Manufacturing Day. We didn't intend for this to happen on this day, but I'm very glad that it did. And thanks again to Ajith also for introducing AI. I'm going to talk a little bit more detail about AI in manufacturing and manufacturing processes in particular. As Rob mentioned earlier, so I'm an associate professor at IFM. Just in the interest of disclosure, I am also co-founder of Matter, which is a spin-out developing AI-based software for the manufacturing industry. So AI has great potential, but also faces quite specific challenges in manufacturing processes. So there's a lot of opportunities for AI in manufacturing because manufacturing features a lot of repetitive and strenuous, dangerous tasks. Processes are quite complex, and AI techniques tend to be very good at making sense of complexity. One of the ways in which AI can add value is by optimizing things. And certainly manufacturing is very resource intensive. Everyone's trying to be more sustainable. And so AI could enable more resource efficiency and therefore help sustainability in the sector. And as you can probably gather from what Ajith said, data is really the lifeblood of AI, and manufacturing can produce an awful lot of data. And in fact, in the chart there on the right, you can see that according to one study, at least, the manufacturing industry produces more data than any other industry. So there you go, lots of potential. But it also faces significant challenges. So legacy systems are in widespread use. Data is very important, but it can be difficult to get data out of those sorts of systems, particularly in the kind of form that you would want for an AI system. Because manufacturing can produce a lot of data, it can be difficult to prioritize what it is that you need to keep and what you can delete. And also it can be challenging to, if you were to do, for example, supervised learning, to label the data that you have. If the AI system, they're not always that robust. If something goes wrong, then it can have quite significant consequences in some cases. You know, if you're making a hip replacement, for example, you don't want that to break. Whereas if you're making a video game, maybe it doesn't matter so much if your AI makes some mistakes here or there. Delivering energy and the energy cost associated with AI in manufacturing can be challenging. So the AI models can obviously take a lot of energy to train, but then also in order to get data in manufacturing, you often need devices on the edge and you need to deliver power to those. And then finally, generally, often AI systems work better the more data that you have. A lot of this data is very valuable. You want to keep it safe because bad things could happen if it gets into the wrong hands. But also, AI systems can be manipulated in some cases quite easily through providing sort of poisonous training data. And so you want to be sure about the source of the data that you have as well, because you don't want your system to be tricked in some way. So as Ajith mentioned in more detail, broadly, the sorts of things that AI can do are regression, as in predicting numerical outcomes, classification, which is just predicting discrete outcomes. Computer vision is a large application area of AI, and there AI can, again, do things like classification, so decide whether one image belongs to as one type or another. Detection, so looking for particular things in an image. AI can do anomaly detection, so things like, does this look out of the ordinary? That doesn't need to be vision-based. It can be use any other kind of sensor as well. Generative modeling has been seen a lot of attention recently, particularly with things like ChatGPT, and that essentially develops AI models that can come up with new examples based on things that they've seen. And similarly, also natural language processes, like natural language processing, where the AI works with human language in order to derive insights or of some kind, has seen a lot of developments recently. And you can imagine, given that there are so many different things that AI systems can do, they can be quite useful throughout the sort of design to manufacturing pipeline, all the way from design and, say, material selection, simulation, if that's necessary, pre-processing, through to the actual production process itself and inspection. There will be some later seminars where we cover how AI can be useful for adjacent areas as well, like predictive maintenance, supply chain management, and energy forecasting, and so on. So just to give you some examples of how AI can be useful through different parts of the sort of design to manufacturing pipeline. If you have a complex process or you're designing a new product, you may want to simulate it because experiments are expensive, or it's expensive when things go wrong. Typically, those would involve physics-based simulations, which tend to, while often being quite accurate, tend to take a long time, be computationally expensive, time-intensive, and so on. AI-based systems or data-driven methods can actually reduce the time taken to run simulations. And they can be several orders of magnitude faster than traditional solvers. You can integrate some known physics into AI-based systems as well to reduce the amount of training data that you need to get good simulation results from them. And there are, again, different ways of using AI techniques to model these simulations. But in general, as you'll see with a lot of these AI-based systems, there tend to be trade-offs between the complexity of the phenomena that you can model, the interpretability of the model, which is broadly to say to what extent can you say that the model makes decisions that it does, and also the computational burden of the process. A key question as well, always whenever you're doing these sorts of data-driven simulations, is the extent to which the simulation will generalize beyond the training data, which is to say, the extent to which the data-driven simulation can model things that it hasn't seen before. One other thing that's also interesting to mention, and that if you haven't thought about this area too much in the past, that you may not be so familiar with, but actually these sorts of simulations, so if you're trying to train an algorithm to run some sort of process, often you need more training data than it's feasible for cost reasons, for example, to actually train the system. Data-driven simulations or other sorts of simulations can be a relatively inexpensive way of producing what's known as synthetic data to train algorithms, and then to reduce the amount of real-life experiments that you need to do. To give you some examples of how AI has been used in manufacturing process control, here we have a laser welding process where ordinarily you would probably use a PI or a PID controller, which obviously can work well in some circumstances, but generally welding processes are highly nonlinear. It's difficult to capture those sorts of phenomena using PI or PID and other kinds of traditional controllers. And so in this case, some researchers developed a reinforcement learning process to control this laser welding system. As Ajith mentioned, so a key part of a reinforcement learning system are that it needs to receive feedback as to the state that it's currently in, and then also some sort of reward signal that tells it how well it's doing, such that it can then decide what to do next. In this case, the laser welding system had access to sensor data, so optical sensor data, as well as acoustic sensor data that it was then able to use both to understand the state it was in, understand how good the weld was, and then to use that to learn how to decide what the next best step to take would be. When you're doing these sorts of things, when you're using reinforcement learning, it's always very, very important to select the correct reward for these agents. In this case, they used, I believe it was the depth of the weld, a combination of the depth of the weld and porosity. But selecting that is always very, very important. Another general thing to note about reinforcement learning is that it can take a lot of tries for the reinforcement learning system to start to become good at what it's trying to do. And therefore, it's generally best to use these systems either if you can simulate them accurately and therefore allow it to try lots of times in simulation, or for processes where you can generate very rapid feedback and where experiments are relatively inexpensive. AI and robotics really deserves its own lecture, or its own session. But just broadly to touch on some of the possibilities that exist there, which are obviously very interesting. There are a variety of different learning methods that can be used to control robots. For example, imitation learning, which, as the name suggests, where the robots sort of learn to imitate humans, or learn from examples. Evolutionary algorithms and human-robot collaboration and so on. Some of the things that can be achieved through AI and robotics are object recognition and scene understanding, and also sort of adaptive learning as well. So the AI system can sort of start to learn understanding of the dynamic environments that robots often operate in, learn how to deal with new tasks and how to deal with injuries and damage. Some of the things that have been demonstrated using these sorts of techniques are, for example, reinforcement learning to assemble chairs, and then computer vision to optimize welding paths, depending on, I believe in this case, the orientation of the workpiece. But like many AI-based systems, there are still significant challenges with these. Certainly in general, often robotic data sets are smaller than, for example, the kinds of data sets that are used to train ChatGPT, which is more or less the entire internet. The real world tends to be a lot more complex than simulations. And so it's difficult to develop control systems that generalize well beyond in order to deal with the unexpected things that can happen in the real world. And so often these sorts of systems can find it difficult to be sort of very robust and safe. And then also because the environments they operate are very complex, often the models are difficult to explain. Another area of some significant advancements in AI recently, where that also has great application in manufacturing, is sort of the end of the, or towards the end of the design to manufacturing cycle, which is product inspection. So vision-based product inspection has advanced considerably recently. Often this uses supervised learning, doesn't have to, but generally the way that this is implemented is that you need labeled images for training, which in some cases can be is fine, but depending on the sorts of products that you're trying to inspect, in this particular case, it's a bottle, that can be challenging. A wide range of defects can be detected, location, and so on. The advantages are that it can reduce the need for manual programming. For example, if the product changes, you don't need to hire an engineer to change the rules by which the system makes decisions. But it can also, again, be difficult to verify results, difficult to know why the algorithm made the decision that one part was defective and another was not. And it can require specialized hardware or software. There's been a lot of excitement in terms of AI recently, particularly because of the rise of foundation models and generative models, of which ChatGPT sort of brings together. Foundation models tend to be large models that have been trained on very large data sets and then adapted to a variety of tasks, while generative models have the capacity to create new data based on existing data that they're given. These sorts of techniques haven't seen very wide use yet in manufacturing, but it's sort of very interesting to think about what possibilities may exist, particularly by reducing the need for new data to train systems in manufacturing, because this can often, as we've discussed, be difficult to acquire and label in manufacturing processes. And so I'm just briefly going to talk about one example of this from my own work, where we attached an inexpensive webcam to a 3D printer, a thermoplastic extrusion 3D printer, where you heat up filaments and push it through a nozzle, and the nozzle then moves around a print bed in order to make things. We trained a neural network, which you can see in the bottom of the slide there, to take the images that are produced by the webcam, and from those to infer whether or not the four main parameters or settings that you have access to in the manufacturing process were either too good, well, not too good, too high, too low, or good. And the four main parameters are flow rate, so how much stuff is coming out of the nozzle, the temperature, the lateral speed, and then the height of the nozzle above the print bed or the piece that you're printing onto. We then used the neural network's output to make a closed loop control system whereby the algorithm is constantly monitoring what's coming out of the nozzle and what it looks like, and then changing the printer settings if it detects an error. What that looks like can be seen in this video right here. And this, there are more videos. This is an open access paper that on the previous slide is the link. So there are many more of these videos if you enjoy watching them. But here's where we introduce an error artificially, and then the algorithm notices that the error occurs and it corrects itself. We are running a bit short on time, so I'm going to just move relatively rapidly through that. Interestingly, though, the algorithm was only trained on one kind of printer, looking at the nozzle from one kind of angle and on one kind of printer. But the algorithm was able to generalize, so to speak, to other kinds of printers and even other kinds of materials. And so it was able to detect and correct errors on a different printer with a different nozzle diameter that was looking at the nozzle in a different direction without needing any new training data. It was also able to detect and correct over extrusion, under extrusion, and ketchup and mayonnaise for those who enjoy those sorts of condiments. And so it's an interesting example of how newer machine learning techniques could reduce the amount of data required in order to control manufacturing processes. You can also use these sorts of insights to, for example, develop sort of loosely called digital twins by summing up the readings from the algorithm throughout the part and then getting a map of where defects occurred that you can then in future use to understand where errors occurred and then potentially prevent errors going forward. And so just to summarize and to finish, general tips for implementing AI in manufacturing. So very, very important to define the goals that you have and to define the metrics by which you will judge your progress towards those goals. You need to understand your data. The data really determines how well your system is going to work. That includes sources of bias, ensuring that you deal with privacy correctly, making sure that the data is secure so that your system isn't manipulated in some way, choosing the right techniques. So broadly speaking, probably you want to reduce the have as simple a model as you can that can still capture the complexity that you need to, because generally those will be more easily explainable and will be easier to run. The hardware requirements are much lower. You want to also, of course, validate the system. So make sure that a key point to ensure there is that there's very strong split. So there's no overlap between the data that you use for training and the data that you use then to evaluate the system. That's sort of quite a common error that can give you overconfidence in the performance of your algorithm. And then finally, also make sure that once you deploy it, that you continue monitoring the system in order to make sure that it continues running. And with that, I believe we can move on to the Q&A.
Fantastic. Thank you very much, Sebastian. If you could just stop sharing your screen now so that we show as shows all of our videos. Fantastic. So please use the Q&A section to ask any questions you've got for Ajith or Sebastian. Just before we start the Q&A, we're just going to ask a couple of questions via a poll just to get a bit of audience feedback. So if we could launch the first poll. So just the first one is about the extent of AI implementation in your organization. How would you describe the extent of it? And there's the 4 options. So if you could, we'll give you 30 seconds maybe to fill that in. It'd be good if it's just manufacturers filling this in as well, if possible. Okay, that's brilliant. And we'll close that poll now. And then the second question, if we could just publish that one, Kimberly, is what AI applications are you most interested in? And there's lots of different options there, and that will help to inform kind of what content we put on in the future related to training in AI. So we'll give another 30 seconds for that while you're typing in any answers and questions as well. Fantastic. Okay, if we could end that poll as well now. Brilliant. Okay, we'll just move on to asking some questions now. So the first one that we've got in was just asking Professor Parlikad, about end-to-end digital supply chain twins. How do you kind of build them when there are a range of digital application systems between different suppliers and partners?
Yeah, thank you. In the next webinar, Alexandra will be much more qualified to give a complete, thorough answer to this question, as she is the expert in digital twins in the context of supply chains. But the key thing, as Sebastian mentioned in his last slide, and when you're thinking about developing AI applications or digital twins, it's to really understand the problem that you're trying to solve, and understanding that problem and understanding the data that is relevant to that problem is the key thing. And this is especially important when it comes to a multi-stakeholder problem that you're trying to address, which is what I suppose you are kind of alluding to when you're thinking about digital twins of a end-to-end supply chain, where there are different supply chain partners involved, each with their sets of data, each with their sets of problems, and so on. So that's the key thing. The next big challenge to address is the issue of standardization of data. Every supply chain partner will have their own data models, their own systems, and so on. So standardization of data, when you're trying to pull data across the different parts in the supply chain, trying to answer a question that you want answers to is going to be a big challenge. So standardization is the next issue, and the third, or perhaps the biggest issue in a multi-stakeholder supply chain, is about privacy and security. How are you going to ensure that when supply chain partners share their sensitive data, of course, they will not share the data unless they see a benefit for it themselves. And if you're convinced that there is a benefit for them, how are you going to make sure that the data that is being shared is just enough for the purpose of answering the question, and how you're going to do it in a safe and secure manner? And Alexandra will talk to you more about it. And there's a lot of research that goes on, especially in the context of supply chain, for privacy preserving means of sharing data in order to enable such end-to-end supply chains.
Excellent, thank you for that. I've got a question here from Maxwell about this, both of you. Could you share any examples of successful applications of machine learning to CNC milling or drilling processes? It's quite specific, but I don't know whether either of you have got any examples.
So I do think that quite a lot of currently OEMs in the CNC milling space do collect data from, the systems tend to be sensorized, and so they collect data themselves that I believe that they use to, and presumably use to feed some sort of algorithm. I don't know whether it's a machine learning algorithm to improve the performance of their systems, but I don't know in detail how those work, and I believe often they are proprietary. So I can't give more details on that. Maybe Ajith knows a bit more.
Yeah, so the examples that I've seen are, of course, this comes from my research area, which is predictive maintenance. A lot of the examples that I've seen are based around, say, for example, spindles and bearings, monitoring vibration data, and use that vibration data to determine whether a bearing is going to blow out or not. And so that's the condition-based maintenance, predictive maintenance area where I've seen some successful applications of.
Brilliant, thank you. We're just looking at the time. We've only got a couple of minutes left, so I'm going to have to draw the webinar to close. Sebastian, if you could just share your final slides, and I'll talk through them, just in terms of engaging with the IFM and future webinars that are upcoming. It's the other screen, if possible.
Yeah.
Perfect.
Yep. Okay.
Just go on to
there we go.
Perfect. So just in terms of some of the upcoming webinars that we've got going on Wednesday, the 8th of November, we're going to have this webinar on supply chains and AI. Alexandra Brintrup, who is the Professor at Digital Manufacturing and the lead of the IFM Supply Chain Artificial Intelligence Lab, will be giving that presentation. And then we'll be also looking at AI for asset management and predictive maintenance. We'll be looking at that towards the end of the year, and Ajith will be giving that presentation. And then moving on then just to the next slide. You can also sign up for IFM Insights. I'm sure many of you already are, but that's the latest information in relation to the IFM and what's going on across the IFM in terms of some of the latest emerging reports and trends. Okay, next slide. We've got courses coming up. Many of these are put on by IFM Engage, which is the knowledge transfer arm of the IFM. So there's really interesting courses on road mapping for strategy and innovation. Lots of other courses. We'll send up all of this information in a follow-up email early next week, alongside a recording of this presentation as well. Just also to mention our memberships. So you can see a range of different membership options available to organisations interested in collaborating with the IFM and our industrial partners. And then the final slide. Just to say a massive thank you to everyone for attending today. It's been really kind of insightful listening to both of you, Sebastian and Ajith. So thank you very much for taking your time to put this presentation together. And a thank you to everyone for taking the time to attend today. I hope you have a lovely rest of the day. Thank you.